Hello, my dear friends, and today we get to linear programming, and our goal for today is to consider the basic formulation, the core concepts of linear programming, and to consider several very interesting and widely used applications of this field of application math. And we'll start with general formulation, and generally speaking, all problems with linear objective function and constraints in a form of equalities or inequalities with linear functions are considered as a linear programming. So actually the term programming here refers to the beginning of the development of optimization methods and research. And here we call, for example, this type of problem as linear programming. And there are some widely used formulation. For example, there is a standard form formulation, there's a basic form, a canonical form, but actually that's not our interest for now. And we'll start with a very simple formulation of linear programming of minimization of a linear function, which could be viewed as just scalar, right? Just a constant vector c multiplied by a vector x, which is a variable here, subject to or such that ax transpose ax, is less equal than b. And actually, these things could be considered without any loss of generality, because any linear constraint here in inequality form could be packed in this matrix form. Let's say we have some, I don't know, a1 x1 less or equal than b1, and etc. am xm less or equal than bm. That's it. And typically we have this n-dimensional vector x and m times n matrix A, as well as m-dimensional vector B. So that will be our linear programming in basic form. And if we illustrate it on a plane, we'll have several hyperplanes or even half planes. Take a look at this. For example, this inequality stands for half plane in this figure. For example, this vector a1, you have this solution for the first inequality. Then for the next you have this solution, for example, this, and for fourth is this, for fifth is this, and etc. And that's pretty picture where all your half planes are intersected in polyhedra here. But for sure you can have a case when you have empty budget set here. That's a budget set. Hope you remember that is. And okay, we have this pretty funny, pretty picture and pretty picture. And here we can also plot and draw our vector c. Why do we need to plot it? Because it's actually very illustrative idea to plot. Because if our function, if c transpose x, then the gradient of our function is just vector c. And the anti-gradient or minus gradient of our function is minus c vector, which literally means then if I have vector c and corresponding minus c vector here, that means that if I'll go into the direction of minus gradient or anti-gradient here, I'll go into the direction of steepest descent of our function, which means that going through this direction will decrease my function. Since the gradient is constant here, we have like a clear view on where do we have to go. Here we have to go in this direction as far as we can. That's the minimization of our function, because everywhere the situation will be the same. The anti-gradient here will be minus c, here it will be the same, here it will be the same, so it's a constant field of anti-gradients here, right? And from this picture, it's almost pretty obvious where the solution should be. Somewhere here, right? And actually, this insight is pretty useful for constructing solution ideas to linear programming, and it was used actually. The solution of linear programming lies almost almost always lies on the intersection, on the border, or even at the vertex, right? Here, if we formulate like this polyhedra A, B, C, D, E, the vertex B will be the optimal one. And actually, solution of linear programming will always lie in this vertex, except one like degenerate case when your, let's say, AB side is orthogonal to your anti-gradient direction. Let's say this is AB of your polyhedra, and here you have the same anti-gradient minus C. But still, both vertices A and B are optimal, because the function value should be the same, despite the fact that A and B, in terms of parameter space, could be separated by a long distance here. So the norm of difference between B and A could be huge, while the function value will be the same. So B and A here are optimal points as well. And this idea of searching an optimal solution through the set of vertices is a core idea of simplex algorithm. We'll go a little bit in details slightly after some words and examples a little bit later. So again, here is a standard form of linear programming, but actually this notation of standard form, or for example canonical form, these notations are useful if you're working with some kind of software which require this exact formulation of your linear programming problem. But typically nowadays we do not have these strict restrictions on the form that you need to put to your solver. Typically it can handle with a very huge variety of the formulations. That's why it doesn't matter for us. Let's consider some simple real-world example of a linear programming, which is pretty actual nowadays, right? That's the diet problem here, and suppose we have P products, which could be banana, cake, chicken, egg, and fish, for example. And we have n nutrients here. Like proteins, carbons, fats, calories, vitamins, and etc. For each of these products, we have all information, like in ideal world, we have this information about nutrients, nutritional facts, right? For example, banana has, I don't know, 8 grams protein per 100 grams. Say 12 carbs, I don't know, 3 fats, 100 calories, and some milligrams of vitamin D. Say 3, I don't know, and etc. So we have a matrix of all this nutrition information. But we are to construct a diet or to buy a set of products in a supermarket, for example, that meet some requirements. These requirements could be lower limits or upper limits, for example, upper bounds. Let's say we do not want to consume less calories than some limit, or at the same time more calories at some higher limit, right? So, like in simplest case, our goal is to verify that we meet these requirements. And again, in simple case, we have, let's say, only lower bounds here, that we have to live, we have to survive somehow in our tough days. But the objective function here forming from the cost of each product. For example, banana cost $1 per kilogram, or per 100 gram cake cost $10, and etc. So we have this cost vector function, sorry, cost vector, just cost vector C, of the same shape as the number of products. And our goal is to find a diet which meets our requirements at the same time which minimizes our spending here at the market. That's our problem. And for sure, that's the linear programming, because we have linear objective function and linear constraints here. We'll deal with the problem a little bit later, but now let us think about some more examples here. For example, you can transform equality constraints form to inequality constraints, or you can transform another way from inequality to equality form, or from equality to inequality. That's pretty huge variety of transformations in order to bring the LP from one form to another. That's not pretty interesting for us for now. That's the example of the Chebyshev approximation problem, which is the solution of a linear system in infinity norm. For example, at the same time, we have this sparse fitting approximation. Suppose we are to find a solution to a linear system AX equals to B, but we also want the X vector to be sparse, for example. That's a L1 approximation problem. And let's go to the idea of a simplex algorithm. Actually, considering the simplex algorithm from very basics, that's a matter of a separate lecture, but we'll focus only on core concept here. Again, suppose we have some polyhedra as a budget set. Let's say this A, B, C, D, E. That's our budget set S. Budget set. At the same time, suppose that we have some function to minimize, which is defined by a vector C. Let's say this vector C, which means that immediately vector minus C is the following, which brings immediate obvious conclusion about the solution of the problem. The solution should be vertex B. That's the solution for sure. But what's the idea of simplex algorithm to find a solution? Because if you have a geometric plot of your budget set, probably you are solving too easy tasks, because in real world you cannot sketch this budget set. You cannot like find an optimal solution just using your eyes. That's not the case usually. That's why we have to develop a procedure to find the solution. And suppose we are, and we have like this vertex E as our initial guess. So initial guess is some vertex. Actually, it's not an obvious question how to find any vertex in this polyhedra. It's a complex task and indeed to find a suitable vertex here at your polyhedra, at your budget polyhedra, you have to solve one more additional linear programming problem. But now for idea, we say that imagine that we have this initial guess. Suppose that we have it. What else? We have to choose where to go next. So the idea of simplex algorithm is to check all possible vertices unless we find an optimal one. Idea of simplex: first, start with some vertex, which is not trivial task, and then switch vertices. Okay, switch vertex. I'll write here, select best vertex among available one, which means that here from vertex E we can go through this direction to the vertex A and vertex D, and we just like have to figure out which direction cooler, which direction is the best. And that's pretty easy to understand because the best direction is the greedy direction, and the greedy direction here is such direction that mostly coincides with the anti-gradient direction. So the closer your direction to anti-gradient, the cooler your direction, and you are to select the coolest direction here. So we select here this direction, and our next step in our simplex algorithm is this vertex A. So that is our x1, and we repeat the procedure again. But at each step, at each vertex, we have to verify or check the optimality. We have also a procedure to check the optimality. Check the optimality. And actually, we have an idea to check the optimality, but that's a matter of, again, the separate lecture on the simplex algorithm. So start with some vertex, select best direction to go, and go to the next vertex and check the optimality. If your vertex is optimal, you're done. If not, repeat the procedure until converge. And you actually have to converge, but you can have some problems because like in higher dimensional space, you can have these cycles in your solution. If, for example, you go for one vertex, the second, and return to the first vertex, that problems could arise, and there are tricks to deal with these problems, to deal with degenerative cycles in your procedure, but we are considering only the basic course. Okay, that's it. That's the simplex idea. Go, like, start with some vertex, iterate until you converge, and you have the rule to check the optimality. But that's how to check the optimality, how to start with some vertex, how to do this step. These questions will remain open for today, but if we want to consider a simplex algorithm in more details, we'll go through them later. Okay, and by the nature of a simplex algorithm, in the worst case, it can check all vertices of your multidimensional polyhedra. which means that you can construct a very adversarial example, and it was done by Klee and Minty. So here is a link to the code here, a link to the paper. These guys constructed counterexample to the simplex algorithm in which, starting from one point, it has to go through all the 2 to the power of n minus 1 vertices of polyhedron, which literally means exponential time to converge. And that's very interesting here because, like, there are cases, and that's a clear example of constructing this case, of exponential convergence of simplex algorithm. But in practice, it's typically converged much faster. It converges pretty okay. Like, this convergence is it's okay for most of the problems here, which is illustrated in this problem. Here's the dependence on of the average computational time on free runs and from the dimension of the problem, and orange one is the worst example here, and here is the average random example. And what's interesting here is that we have a log scale, logarithmic scale on the y-axis, which means that, like, here we have clear exponential convergence, right? Because exponential dependence, sorry, because with one step we increase the logarithm of the constant factor. But here also we have something like that looks like exponential or sub-exponential, but much faster than the worst one. And this question is very interesting. Why so happen? Because we have to construct some suitable theoretical explanation for this fact, but it's it's probably not the matter, not the question of our today's lecture, but still it's very interesting problem here. And actually, from the very beginning of the development of this linear programming, which was started in the first half of the previous century, from the works of Danzig, Kantarovich, only simplex method was a single option to solve the problem, and in worst case it could converge exponentially. But MIPT alumni Leonid Khachyan developed a method that was first method to be proved running at a polynomial complexity for linear programming. But the dimension of the problem, starting from which this ellipsoid method works in practice faster than simplex algorithm, is quite huge, like unapplicable huge. And that's why a lot of methods were developed for linear programming, and we even here have very interesting fact about speed of convergence of modern algorithm versus speed of computers. And this pretty interesting story about development of algorithms for solving linear programming and development of a computational power. And the typical question here is like, which one will you choose? Is to run modern algorithms and software on the old machines, versus old algorithms and software on the modern machines. Let's consider these digits. Yeah, let's add a page here. And there was a study by Bixby who studied the development of linear programming solution packages from 1991 to 2007. That was a package that was called simplex package, and that's the Bixby study. And interesting that during this period of time, the same set of, like, he ran a very huge set of almost 2000 of linear programming problems and ran it through the all versions of this package, and total increase in performance on the same machine was about 29,000 times improvement. And there are even like the fastest time and the highest acceleration of the solution was in the switching between one version to another in this 1998 year, where a lot of theoretical things were implemented at once, and here was about 10 times acceleration, which was the highest acceleration at the time, like per version, but cumulative acceleration was about 29,000 times. And later there was a Gurobi package, which like increased this performance 16 times more. So here was Gurobi, and improvement was about 16 times versus this simplex version, up to 20 and 12 year, which means that the total acceleration, which is related only to software and new mathematical ideas here, was about this. At the same time, have a Moore law, and the CPU acceleration here, or like a hardware acceleration, let's write in this way, hardware acceleration at the same time was only about 8,000 times, which means that it is much faster to use old computers with modern software and algorithms rather than using modern CPUs and old softwares. So that was progress due to new algorithms and ideas, and that's pretty interesting, pretty fascinating. I can leave a links to these examples and studies if you want to, but that's very interesting to read, very interesting story for me. So our choice is to select modern algorithms almost always. So the development of math is faster and cooler than the development of semiconductors here. Now let's go through some practical examples of interesting linear programming application. Okay, here we have the notebook with some stories about linear programming, and we'll start with how to solve linear programming with SciPy, which is pretty easy to solve. Here we have very general formulation of linear programming. We have some linear function C transpose X subject to AX less equal than B with additional restriction on the second entry of X, which should be greater than -3. And here we can just, you can see, set the vector C, matrix A and vector B, set the bounds on the first entry of X and the bounds on the second entry of X. So X is a two-dimensional vector here because A is also 2 by 2 matrix. And we just import limproc function from SciPy optimize and put this vector C, put our function, our linear function here, and these arguments such as A upper bound, B upper bound, and exact explicit bounds on the parameters. So that's a primal feasibility, dual feasibility, duality gap, and we can see that we have successfully solved this problem. Number of iteration, the function value, the total number of iteration, but actually we do not know exactly which algorithm was used here. That's why I'll specify it explicitly and ask SciPy to use simplex algorithm for sure. Simplex algorithm. And we'll take a look and we have less, like lower number of iterations, but still optimization terminated successfully, which means that we found a solution here. That's the example of Klee and Minty with the worst case scenario for linear programming. And here you can see this picture that was shown to you as a previous part of the lecture. That's one more interesting case about the diet problem, and we are to solve this problem. We're going to solve it exactly for some specific choice of nutrition information and price vector. So again, the formulation, and we've added one more important restriction here, that each x should be greater than 0, which in fact means that we can only buy a product in our market, not a sell it or not a borrow it, right? Okay, let's go further. Okay, here we are formulating our objective function, which is just a scalar product between those two vectors. Here we have some constraints like a minimum value of nutritions and the maximum value as well. Then we will use PyOma library to find an optimal solution for this problem here. Here we use just installation of these libraries. It takes time. Okay. Next, we will initialize our model as an abstract model here from PyOma. Okay, that's an object from the library here. You can see that we've imported everything from PyOma. Now we specify our sets about foods and nutrition here, and here's the vector of cost. Here is the amount of nutrition, and as I said, okay, first I have to run previous cells. That's it, that's it, and that's it. Now we formulate our variable here, which is amount of each food that is needed to be consumed. Here we formulate our cost function or objective function, which is linear. You can see it. Here is the sum of these pair products. And at the end, we put everything together to the files which were already prepared in advance, but still we can see this file with the program itself. That's it. Here's the file. You can see it. Model, all definitions, all cost functions, all constraints are formulated here. But also we have a data file. Here we can see these metrics. That's a matrix of all nutrition information like cheeseburger, calories, carbons, proteins, and etc. Here is our upper and lower bounds. For example, we do not want to carbons be higher than this value. And also we have this cost vector as well as volume vector. For example, we are to construct a diet with a limited volume. Let's say, let's take a look here. Here we have a restriction on the maximum volume of food consumed. It's pretty reasonable. And now we just run the solver and defining explicitly the programming part and the data part. Here are two files, and we run it. And that's it. Less than a second takes to solve this problem from the scratch. And the results were written in the file results YAML. Here we can see number of objectives, constraints, variables. It can handle even how to say integer variables, right? Yes, that's written here. Solver status and time that was taken to solve it. Optimal solution, we have the cost function and optimal value for each variable. We have 4 cheeseburgers, 1 fish sandwich, 5 fries, and 4 low-fat milks. And actually, what's interesting here is that despite the fact that we didn't explicitly wanted our variables to be integer, I mean in our talk, in our program we specified it. And let's take a look. Yeah, you can see this for the nutritions. Yeah, non-negative integers. And actually that problem is harder than just real numbers. And we'll take a look at other versions of another version of formulating this idea with real numbers. Let's consider one more interesting example here. This is about transportation networks, which is pretty practical one, right? And the problem is the following. Suppose we have some manufacturers and some consumers of some, I don't know, products, materials, supplies, I don't know, anything. And let's say here, blue one are producers and the red one are consumers here. And each consumer has its own demand on the material, and each supplier has its own limit of like production limit per day, for example. Yeah, here we can like put all this information to a table. For example, we have 2 cities here, these Arnhem and Gouda city, which are producing something in the amount of 550 tons and 700 tons, let's say per day, for example. I don't know, it doesn't matter here. And we have the consumers of the product. For example, Berlin needs 175, sorry, Berlin needs 175 of tons of this thing. Maastricht wants this amount of tons of this. And here are the prices of transportation from producer to consumer. For example, here are NA stands, which means that it's stupid to transfer materials from Arnhem to London, because Gouda is closer to London, and that's why here we have this value. But when we are talking about, for example, Utrecht, it's not pretty obvious from which producer you should supply the material. For example, here we have this Utrecht, and we have these different prices. That could be a matter of roads, of logistics, and etc. So we'll formulate a cost function here, and the cost function is following. We'll sum among all customers and among all sources the amount of transportation between the customer and the source. So we actually have a matrix of flows between all customers and all flows, and all sources here. At the same time, we have this matrix of the price per ton. Also have some limits here, and take a look. Despite the fact that we have a matrix here, matrix of variables and matrix of data with the same shapes, the cost function is still linear. What about the restrictions? For example, if we're considering that for each source, the amount of materials that this source can produce should not be higher than its limit, right? So we cannot produce more than our capacities. And the same constraint on the customer, that the total sum of for each customer, we have to meet its demand, right? And that's also a linear constraint here. So we have linear objective and linear constraint. That's linear programming, and that can be solved using all these linear programming packages, software, and etc. That's pretty cool for us. We're building Pyoma model here. That's the data here. And for example, we can see some strange thousands here, and these thousands actually replaced, they are replacing this NA, because if the cost for transportation from Arnhem to London cost 1,000 euro per ton, while the same way from Gouda to London costs some 2.5, right, per ton, it's actually something similar to NA. Okay, then we'll put the model file here, and here we build a concrete model with concrete values. We build a cost function, we build a variable here, we build a list of source and a list of customers, and we solve a model. Oops, name demand was not defined. That's why we run it here. That's the problem information. Here we have 9 constraints and 13 variables. And we solve this problem. That's the time for solution, and pretty important logistic problem, right? And that's the total answer here. So the optimal transportation plan was built using linear programming, which is cool. Here is the total shipping cost. And that's the optimal picture for transportation. So, like, when you have actually 2 suppliers and let's say 6 customers, that's not pretty easy to solve by hand, but computer can solve it like almost instantly. And finally, we'll consider an example of production plans, which initially were the problems that inspired the development, the rapid development of linear programming and corresponding algorithms. Suppose we have some factory that produces product X, and we have a demand for this product, and we can sell this product by some price, right? So our final goal was to maximize a profit, which is a revenue minus cost for production. The more we produce, the more cost we have, and the more revenue we have, and we have to maximize it. So the cost is split between some inputs like raw material, cost of labor. For example, we have 2 types of labor, I don't know, production and marketing, let's say. And let's say we have X amount of product, which means that per each product we spend $100 of raw material, $50 on labor A, and let's say $80 of labor B. So the total is $230 per each production unit. And we sell it for $270 per unit. That's why our profit is $40 per one production unit. And our goal is to maximize this, and it seems pretty obvious that if our production is profitable, like we have to produce as much things as we can. And that's the right answer here. But we also have a limit. For example, our workers cannot work more than some amount of time per week, let's say. Or we have some limit on raw material. That's why we have to play with it, and for the very simple formulation, like the answer will be obvious. We have to produce as much as we can. But what about a second idea? For example, we have labor R, and we have actually 80 hours available of worker, right? That's like 2 worker of full-time work week here, and here we have a price of an hour, and the same for labor B, for example. And we have some limit. For example, limit on the, here we have this, the amount of like working hours per week cannot exceed these numbers. Okay, and we'll immediately like have the answer. But what if we have a mixed product? That's interesting actually, because suppose we have different products, like product X and product Y, built from the same actual inputs like raw materials and 2 types of labor here. And that's the play, which one you should produce more and in which exact amounts. That's actually the linear programming problem. And here is the answer to this linear programming, and the notebook is available by this link here, or you can just go to our site, and that was a short link to it. And here we have an optimal plan that in order to maximize our profit, we have to produce 20 units of X and 60 units of Y. not like an equal part production. And here are some graphs which are reflecting this production strategy, which means that if we would only produce a next product here, we could produce only 4 products per week. If we would only produce Y product here, we would only produce 80 products per week. And these answers were not optimal in a sense of maximizing a profit. That's pretty interesting here. And the last but not the least example of beer blending problem. Suppose you have like several types of beer with each own alcohol by volume indicator. For example, this is ABV, alcohol by volume. Some Ochota beer, Baltica beer, and water, which is not a beer, which has 0 alcohol per volume, and each own cost. And suppose you are to blend these beers to find an optimal beer with the desired properties, for example, for alcohol by volume and for cost. That's why you formulate your objective function here. You are to minimize the cost of the total blending, and you have the volume constraint here, that because like for example, the customer came to your brewery and asks for a drink of a specific value of alcohol by volume and amount like 1 pint or like 1 liter. Why I'm talking about this example? Not because that's very like intellectual example or very solid linear programming famous problem. No, because that's interesting story about optimization. Because if we have this limit, for example, we have to blend something and we have to maintain some average level, for example, of alcohol, or I don't know, some mixtures and etc. It doesn't matter for now. This constraint, if it's written in the following way, for example, the total sum divided by the total weighted sum divided by the total sum should be equal to some level, like alcohol level. This constraint is not linear. That is what's interesting here. But if you multiply both right and left hand side here on the same sum, you'll actually immediately obtain linear constraints, which means that the same actual formulation, the same problem could be formulated in a linear programming way and solved easily, and in some non-linear way. And in this case, you cannot handle it with LP solvers. That was interesting part here. And so we can just solve this data, right? We have to again put it, run it. So we have some specific answer here. And what is about mixed integer programming? And I suppose that's a matter of separate video here. Okay, that's all for today. The link is available here in our site, in our repository. Thank you. Bye.